Hello, I'm Raf, the head of the Imperial Planetary Robotics Lab, IPRL, and I'm thrilled to announce our latest rover, Bobtopus, designed and developed here in the Imperial College Robotics Society at Imperial College London. This year, we've made several updates that we are very excited to talk about. Our team consists of 33 dedicated members, and I'll now pass on to our project managers, Azad and Alex, to explain in further detail how this is structured.
Our team comprises of 30 members operating in 11 specialized groups. These sub-teams focus on the dedicated rover systems. Drive, chassis and suspension works on our modular structure and mobility, the robotic arm for the manipulation and maintenance tasks, and drilling and payload for deep sample extraction and storage.
The electronics team designs our custom PCBs and manages power, while the autonomous navigation team handles our main software stack. The UAV team is building our custom drone, and the science team manages the astrobiology tasks. Finally, everything is kept organized and on track by our marketing team, project managers, head of IPRL, and our technical advisors.
IPRL was born from a mission to empower the next generation of engineers to tackle the biggest challenges in space robotics. We aim to offer our members the experience of working towards real, tangible goals, giving them ownership and pride towards their creations. Today, we are excited to showcase our hard work, which is a testament of our growing commitment to ERC, having now competed for 3 years in a row. Solving real and meaningful problems sits at the heart of our engineering philosophy. ERC provides us exactly the right situation. The difficulty of navigating the unknown Martian terrain excites us. This is reflected in the design and passion of our rover and UAV teams, which we are about to show you.
2026's DCS system builds upon the successes of the previous year whilst making modifications and overhauls where necessary. The differential bar and chassis were kept from last year's rover, with their weight and modularity allowing for rapid modifications to the rover spec between tasks. A large focus for this suspension was reducing the vibration that the chassis experienced, particularly during turns, and as a result, rigid connections in the differential bar were swapped for damping shock absorbers. The rocker bar design was kept largely the same, with the main differences being weight-saving measures. The previous rocker bar used steel components, solid plates, and bulky rocker bearings. These were stripped back using informed design and stress analysis to result in a rocker bar system 2 kilograms lighter than last year. The largest overhaul came to the drive system, where component failure led the team to switch to a BLDC motor system to increase torque and facilitate driving. These motors drive a 1:20 planetary gearbox, allowing for increased torque, less backlash, and better reliability when navigating the rocky terrain and inclines.
Wheel assemblies have been reinforced to improve durability under repeated dynamic loading. We increased engagement between the wheel hub and rim to distribute torque more evenly and reduce localized stress concentrations that previously led to cracking. We introduced a machined aluminium reinforcement ring at the hub-rim interface to increase stiffness and improve fatigue resistance. We also integrated a new modular camera mounting system to support autonomous navigation, allowing reconfigurable positioning of the cameras on the aluminium T-slot chassis.
For the drive system, one of the main changes this year is we've switched to using brushless DC motors, whereas last year we used DC motors. So that's resulted in a significant change for the motor drivers, and we've decided to link those up using a CAN bus, and we are running the motors using field orient control using absolute magnetic encoders. This year we use 4 LiPo batteries to power the rover as opposed to the 1 LiPo battery we used last year. This has 2 main advantages. Firstly, it increases the maximum battery capacity of our rover, but it also means that because we have 4 LiPos, we can charge them in parallel as opposed to charging 1 large battery, which enables a shorter turnaround to bring the rover back up to full charge. The power board also incorporates an emergency stop button, which cuts all power to all of the subsystems of the rover so it stops moving. We also have voltage and temperature sensing to make sure we look after the LiPo batteries properly, and we also have current monitoring to help estimate how much current the rover's drawing and how much longer we can run for in a task should we use a lot more current than expected. For the communication system, we have switched from a Wi-Fi based approach that we had last year, which resulted in high latency at ERC, to an AirMax 5 GHz solution, which has much higher data throughput and will hopefully reduce the amount of latency that we see at the competition. We have chosen a sectored 120-degree antenna for the base station, as it will help reject noise not coming from the Mars yard, and an Omni antenna for the rover due to its 360-degree nature, so we can always connect to the rover no matter its orientation. These will act as a bridge between the base station and the Raspberry Pi on the rover, and should this not function at all times, we will have a backup communication system using LoRa for the controls and wireless HDMI to send the video stream. The rover's electronics is designed so that each subsystem has its own ESP32, which is responsible for all the low-level behaviors of the subsystem. We have a main central Raspberry Pi which receives data from the base station over ROS, and that then sends those high-level commands across to the ESP32 to control the rover.
2025 UAV provided a strong baseline for the team, but it also highlighted several key areas for improvement. In particular, we identified opportunities to reduce mass, improve structural reliability, simplify manufacturing, and enhance autonomous navigation performance. The most significant changes this year were made to the airframe. While we retained the stacked carbon fiber quadcopter architecture, the arm, leg, and plate designs were all significantly overhauled. The arms and legs were redesigned from a truss-based structure into more simple tubular members. Although this slightly increases the part count, it provides a cleaner load path through the structure and makes the airframe more modular. This also makes the UAV easier to repair, modify, and upgrade between testing cycles. The plate design was also refined to reduce unnecessary material and designed around packaging of the onboard electronics. Overall, these changes have resulted in a 20% reduction in total mass and a more compact UAV. This directly improves the UAV's thrust-to-weight ratio and flight characteristics. For the sensors and electronics, most of the system was retained from last year to reduce integration risk. However, the motors and batteries were resized to achieve a more reliable 2-to-1 thrust-to-weight ratio. This gives the UAV sufficient performance margin for stable flight. On to you.
Our system has 4 main parts: the Raspberry Pi wide-angle camera, MATLAB on the laptop, the optical flow and range sensors, and the Pixhawk 6C flight controller. The Raspberry Pi camera sends live video, and MATLAB processes each frame to detect the Orca marker, which is our landing target. Using the target following algorithm, MATLAB measures the marker position relative to the image center and converts the error into horizontal 2D movement commands. The range sensor is used to control height so that the drone first arms and climbs to a fixed altitude. The optical flow sensor helps estimate motion relative to the ground, which improves hover stability and makes the horizontal following smoother. MATLAB sends the movement commands to the Raspberry Pi, and the Raspberry Pi forwards them to the Pixhawk through the MAV SDK in off-board mode. The drone keeps following the target, and once the marker is centered closely enough, the system decides that the drone is above the landing point and commands it to land.
This year, we completely redesigned the robotic arm, eliminating the 4-bar linkage from previous versions. Instead, we moved to a direct drive arm with a motor at each joint, which greatly simplifies the mechanics. The structure is built from carbon fiber tubing, with each linkage bonded to the next using aluminium inserts and industrial adhesive. And for easy disassembly, the whole arm clamps directly to the shoulder joints. At the end of the arm sits our end effector, a differential wrist that gives us 2 degrees of freedom in a single joint. This connects to a high-speed, high-torque gripper, and its fingers can be swapped out to suit whatever the task requires. The entire system runs on ROS2 and MoveIt, which handles smooth trajectory planning, translating our controller inputs into precise physical movements. Driving all of this is a custom PCB, and onboard ESP32 reads data from our custom encoders over I2C, then sends the right signals out to the separate motor drivers and servos.
Our drone and payload system is designed for 2 key tasks: sample extraction and sample collection. To collect deep samples, our drill system uses a linear actuator to drive the drill assembly into the ground, while a separate motor spins the auger for soil extraction. These 2 motors are synchronized for smooth and reliable drilling. This year, we improved the drill system by increasing structural rigidity and reducing vibration for more stable operation. For deep sample collection, we replaced last year's actuator brush with a fixed brush design, making the system simpler and more reliable. Finally, we also upgraded the sample collection boxes with larger capacity and magnetic attachments for easier handling.
For the drill system, it uses 2 DC motors, and we use a control system to sync up the speed of the rotation for both the auger and the drill to maximize the torque output of the drill. We've also switched to using a stepper motor for the payload over a servo motor that we used last year due to the servo motor's unreliability in the potential heat of ERC.
Well, that's it for our 2026 Bobtopus rover. I'm very proud of what our team has managed to accomplish this year, and we hope you get to see it in action this summer on the Mars Yard. Thank you to our supporters who made this even possible in the first place.